Hello, I'll be talking about here the practice exam for Unit 10, which is about stoichiometry. So in this first section, I'm just doing some simple problems using mole ratios. That is the stuff that comes from the beginning of this unit, so hopefully it shouldn't be too hard. In each of these problems, you'll need to balance a chemical reaction and then perform a mole-to-mole conversion, but that's all that we'll be doing. I'll also note that this is the only section of the test where you'll be balancing reactions. For all other sections of the test, the reactions will be given to you already balanced. So in this first one, I'll start off, as I said, by balancing it. It's not too bad. To do this one, I need a 2 here, a 2 here, and a 2 here. All right, and then everything should be balanced. 2 sodiums on each side, 4 hydrogens on each side, and then 2 oxygens on each side. So once we have the balanced chemical equation, we can do the mole conversion. In this one, it says you start with 4.3 moles of sodium and asks how many moles of hydrogen are produced. So you start 4.3 moles of sodium. Then we use the mole ratio of the coefficients to convert from moles of sodium to moles of hydrogen. It's 2 moles sodium because that's the coefficient there. For every 1 mole of hydrogen because that's hydrogen's coefficient. All right, and then we just have to calculate it there. And you get 2.2 moles of H2. 2.2 moles of H2 produced. Put that answer in the box. 2.2 moles of H2. Okay. For the second one, again, we have to balance it. This one's even easier. All that you need for this one is a 2 in front of HCl, and things are balanced. So again, it gives us an amount of moles, in this case of HCl, and it asks how many moles of zinc were used up. So we have 2.35 moles of HCl. And we want to cancel out moles of HCl and get to moles of zinc. We use the mole ratio for that. We know that there are 2 moles of HCl for every 1 mole of zinc. This is by looking at the coefficients from that balanced equation. Calculate that, and you should get 1.18 moles of zinc. 3 sig figs in our answer. And actually copy this over again, 1.18 moles of zinc. The bottom part here, these are 2 problems that are more stoichiometry proper problems where you're going from units of one substance in the chemical equation to any units of anything else in the chemical equation. It gives us the photosynthesis reaction, and it tells us that we have 3.65 times 10 to the 19th molecules of CO2, and it asks us to calculate the mass of O2 that's produced. So we're going from particles of CO2 to the mass of O2. So the first thing here, we're going from grams to moles in this problem for O2. We start with molecules of CO2, and then we go to moles of CO2, and then moles of CO2, we go to moles of O2, and then moles of O2 to grams of O2 because it says what mass of O2 is produced. So that lets us know that we have to have the mass of O2, the molar mass of that calculated. It is 32.00 grams. You look that up on the periodic table. So we start with what they give us, 3.65 times 10 to the 19th molecules of CO2. Then we want to get out of molecules of CO2 and into moles of CO2. Molecules to moles, the conversion factor is 6.02 times 10 to the 23rd, so 6.02 times 10 to the 23rd molecules of CO2. in 1 mole of CO2. All right, then we want to get out of moles of CO2 and into moles of oxygen. So looking at our balanced chemical equation, we know that there are 6 moles of CO2 for 6 moles of O2. Those are just the coefficients. All right, then as a last step, we know that in 1 mole of O2, we have 32.00 grams of O2. If you calculate this and round your answer to 3 sig figs, you should get 0.00194 grams of O2. All right, on for problem number 2 here. It says a chemist is using a propane grill to cook a hot dog. She begins to wonder about her carbon dioxide emissions and finds that she used 392 grams of propane to cook her lunch. She wants to know how many liters of carbon dioxide were given off by this process at STP. So in this one, we're going from grams of propane to liters of CO2. Thinking about the process we're going to take in our head, we're going to go from grams of propane to moles of propane. That means we're going to need the molar mass for propane. All right, then we go from moles of propane to moles of CO2, and then from moles of CO2 to liters of CO2. So first, let's calculate that molar mass for the propane. It's C3H8. If you find those masses on the periodic table and add them up, you should get that it is 44.11 grams. All right, so now we start with our 392 grams of propane, 392 grams of C3H8. We know that there are 44.11 grams of C3H8 in 1 mole of C3H8. All right, now we're in moles of propane. We want to get out of moles of propane and into moles of CO2. Looking at the balanced chemical equation, we know that for every 1 mole of C3H8, that there are 3 moles of CO2. That's just from the coefficients. And then we're going to go from moles of CO2 to liters of CO2. So we know that for every 1 mole of CO2, there are 22.4 liters of CO2. If you calculate that and round your answer to 3 sig figs, you should get 597 liters of CO2. For part C, we are going to do a limiting reactant problem. It says there are 2 things that are going to happen here. We need to identify the limiting reactant, and we need to determine the mass of the product which is produced. Okay, so this one involves 2 different stoichiometry problems. I'm going to grade you on both of the outcomes, and so even on the reaction that doesn't end up happening, I'm still going to look at your answer for that one as part of your grade. So we're going to start off here. As a general process for this, what happens here is we're given the masses of both of the reactants, and we need to figure out how much of the product we're making. All right, we need a lot of molar masses in this. So I need the molar mass of silver, that's Ag, and for that, if you look it up on the periodic table, you should see 107.87 is the molar mass. Okay, we need a molar mass for I2. If you find that on the periodic table, you should find it as 253.80 grams. And if you look up the mass for AgI, you should find that it is 234.3 0.77 grams. Okay, so as I said, now we're going to do two stoichiometry problems. One starting with the grams of silver, one starting with the grams of iodine. We're going to see which one produces less of our product, and that's going to be the one that we go with. So starting off here, 99.5 grams of silver. 99.5 grams of silver. Okay, in the first step, we need to go from grams of silver to moles. So looking at the molar mass, it's 107.87 grams of silver in 1 mole of silver. All right, in the next step, we need to go from moles of silver to moles of our product, which is AgI. So looking at the balanced chemical equation, you see that there are 2 moles of silver for every 2 moles of AgI produced, so it's a 2-to-2 ratio. And then lastly, we need to get to grams of AgI, so we go moles to grams using the molar mass. We know for every 1 mole of AgI that it is 234.77 grams of AgI. If you calculate that, you should get 217 grams of AgI. 217 grams of AgI. That is rounded to 3 sig figs. But we have to do this whole process again now for iodine to see how much we could make given 125 grams of iodine to start with. So we say 125 grams of I2. For iodine, getting from grams to moles, we know that there are 253.80 grams of I2 in 1 mole of I2. Then we need to get from moles of I2 into moles of AgI, looking at the balanced chemical equation with our coefficients. We know that for every 1 mole of I2, we have 2 moles of AgI. And then we're going to get from moles of AgI to grams of AgI again, so we use the molar mass. 1 mole of AgI has a mass of 234.77 grams of AgI. If you go through and calculate that and round your answer to 3 sig figs, you get 231 grams of AgI produced from that reaction. All right, and so we have to think about this and what it means in terms of limiting reactants. What this says is we have enough silver to make 217 grams of AgI. We have enough iodine to make 231 grams of AgI. And so what happens here is we actually end up running out of silver first, all right, which means that this 231 never happens. Our answer here is that we make 217 grams of AgI because silver runs out first, and we end up with silver as the limiting reactant. So the limiting reactant here is Ag, and the amount that we make is 217 grams of AgI. Okay, for the last problem here, it is a percent yield problem. On this one, what we have to do is we have to do a stoichiometry problem, which then calculates the theoretical yield. Then once we have the theoretical yield, we take the actual divided by the theoretical times 100. If you look through this problem, it says a factory is trying to produce ammonia and H3 for use in fertilizers. The company starts with 42 grams of nitrogen and excess hydrogen. They are able to produce 2,932 grams of ammonia. What is the percent yield? So in this one, what's nice is it says that there is excess hydrogen. If there's excess hydrogen, that means that we don't have to do a limiting reactant problem on this one. It's just going to be one stoichiometry problem to calculate the theoretical yield, and then we can go with that. We are given the amount of nitrogen that we start with, and then it tells us how many grams of ammonia that we collect in the end. This grams of ammonia here, you should identify that's the actual yield, all right, because it gives us grams of the product that we are actually able to collect, all right, and that is called our actual yield. So we start here on a percent yield problem with the amount of our reactant that we're given. We're going to need to know the molar mass for both N2 and NH3. So if you calculate that from the periodic table, or if you find it on the periodic table, for N2 you should get a mass of 28.02 grams. And for NH3, if you calculate its molar mass from the periodic table, you should get 17.04 grams for NH3. Then what we're going to do is we are going to start with the amount of nitrogen that they give us. That's 25.42 grams of nitrogen. 2,542 grams of N2. And we're going to try and get to grams of NH3 that we would produce. First, we have to go from grams of N2 to moles of N2. So we know that there are 28.02 grams of N2 in 1 mole of N2. Then we know for every 1 mole of N2, this is looking at the balanced chemical equation going from moles of N2 to moles of NH3. So we look at the coefficients. We know for every 1 mole of N2 that we produce 2 moles of NH3. All right, now we need to get from moles of NH3 to grams of NH3. So we use the molar mass. 1 mole of NH3 has a mass of 17.04 grams. If you go through and do that calculation and round to the appropriate number of sig figs, you should get 3,092 grams of NH3. In this process, then, this is known as our theoretical yield. All right, the stoichiometry always gives us the theoretical yield. We're given the actual yield in the problem, and so to find the percent yield, we do the actual over the theoretical times 100. Okay, in this case, the actual yield was 2,932 over the theoretical yield, 3,092 times 100. And we end up with 94.83%. I will note that this was given to 4 significant figures in our percent because all of the calculations in this problem had 4 sig figs. If, as you went through this practice exam, you struggled with any bit of this, I recommend that you look back at the previous worksheets and previous videos that are touching on whatever concept you're struggling with. And if you can't figure it out that way, as always, come in and ask.